Hello, my name is Sevgi Gurbuz. I'm an assistant professor of electrical engineering at the University of Alabama at Tuscaloosa in the United States. I'd like to welcome you to my talk, which is entitled ASL Recognition Based on Kinematics Derived from a Multi-Frequency RF Sensor Network. This work represents a joint collaboration across faculty who cover 4 different departments actually, not just electrical and computer engineering, but also computer science, communication disorders, and communication studies. Significantly, it was done with the collaboration of academics as well as the community who are deaf and are involved with deaf education and different programs targeted towards the deaf community. This includes the Alabama Institute for the Deaf and Blind, which is located in Talladega, Alabama, as well as Gallaudet University in Washington, D.C., which is, to my knowledge, the only deaf university in the United States where ASL is used as the primary mode of instruction across all classes in the university. The main motivation for our research has to do with trying to basically investigate RF sensors as a new modality for the purposes of ASL recognition. Even though our research currently is focused almost exclusively on RF sensing, in my opinion, towards the future, this is a sensing modality that can be fused with other types of sensors, such as wearable sensors and optical sensors. If you look at these sensors, each sensor has its kind of own unique advantage as well as disadvantage. The main advantage that RF sensing brings to the table is the fact that it's non-contact, protects privacy, and can also capture some kinematic features that are maybe not as easily captured or effectively captured by some of these other modalities. Furthermore, RF sensors can operate in the dark and through the wall, and depending on the type of antenna you're using, direct line of sight might not be required to gain some kind of sensing capability. So from that perspective, it's a really interesting sensor to look into. Another reason for why this sensor, I believe, is so important is because of the fact that it strikes very well with the deaf community in general. In focus groups that we've held with members of the deaf community, where we've discussed with them technology, the types of technology they use, and what they think the benefits or the disadvantages are of existing technologies for deaf people, they expressed a lot of concern over the protection of privacy. They want to be able to use technology, but they don't want to feel like they're constantly being monitored or surveilled just for the sake of being able to have, for example, an ASL sensitive smart environment. And they also don't like technologies that interfere with their daily behaviors, such as wearables, gloves, and similar kinds of devices, which really affects the ability of them to use their hands in the course of daily life. So to kind of summarize the way that we did our work, we set up a multi-frequency sensor network in the lab. Even though multiple sensors is not necessarily required for the purposes of ASL recognition, we wanted to see how performance varied across the different types of transmit waveforms and frequencies that are available from different RF sensing devices that are commercially available. So we basically set up this kind of a corner placement of the sensors where some of the sensors were placed directly facing the individual and others were skewed and elevated off to the side, while we had yet another one that was observing the person from basically the cross range position, so sideways. And on the right hand side of this slide, you can see the way that we've placed the monitor, which basically has different kinds of prompts. So when we brought the participant into the lab, the monitor already expresses the types of words that we want the person to sign, and the person just kind of follows along with the prompts given in the slides and enacts them. And during that time, we collect data from all of the sensors that have been indicated in this diagram. One thing that we've observed in the course of doing our experiments is that there really is a strong difference between sign languages as observed from imitation signers. These would be people like myself who are hearing individuals and who could potentially watch a video of sign language and then try to imitate that sign, versus the signing that's done for a native individual. On one level, this seems like it could be an obvious distinction. We all know that anyone who speaks a foreign language, if it's not their native language, then they have their own accent. In the case of American Sign Language, this shows up as differences in kinematics, which are incurred to the fact that we don't really know exactly how to do these signs, or we're not exactly as fluent, and therefore we can't really do them with the same kinematics and the same dynamics as someone who's a native signer. And this was a fact that we have discovered by analyzing the data as well. You can design a machine learning algorithm, and we have done this, which using support vector machines can completely and identically distinguish whether a person is a native signer or not. And if you look at the samples of the data, you can actually also observe in the radar signature errors that occur due to not knowing how to do the signing very well. And this could be things such as incorrectly repeating the number of repetitions and doing a sign like knife, for example, and other things. There's a lot of jerkiness sometimes in the way that native imitation signers reenact these signs. And so I think it's significant that we did our study on native signers. And so the results that I'm going to present to you today are from data that's acquired from 3 native ASL users who were deaf. And in this initial pilot study, what we did was we asked them to do 20 different ASL words with different numbers of repetitions so that there was statistical variation in the data. And what I'm showing you on this slide is what we call the micro-Doppler signature, basically the time frequency transform of the RF data that we receive. And you can notice some gross features of the data. So for example, you can tell by observing the RF signature whether the sign that's being done is a single-handed sign versus a double-handed sign. You can tell, for example, whether the motion is being done in tandem, so something like breath, for example, where the 2 hands are moving together, or if it's something where there's asynchronous motion. You can tell, for example, whether the hand is directly facing the radar or is kind of skewed relative to the radar, because you can see differences in the received signal power. And of course, you can very clearly notice different types of periodicities, such as when there's a repetitive motion, and you can notice that the Doppler spread of the RF data is reduced when you have tangential motion. So this would be motion that would be perpendicular to the radar line of sight. And in cases of occlusion, there are some signs where there is self-occlusion. One of the hands is masking the motion of the other hand. You can also notice these kinds of effects in the radar data because, again, it blocks your observation of the full form of that motion. So I think it's significant that you can see so many of these features in the RF data, and actually we can also see effects such as co-articulation. This would be slight differences in the shape of the sign due to the fact that it's located grammatically in different parts of the sentence, which therefore changes the starting position from which the sign kinematically begins. So there's a very strong correlation with kinematics in the signs, and RF sensors are very capable of picking up these sorts of differences. For the purposes of this initial study, though, we just wanted to do a pilot study to see if we could accurately discriminate, let's say, 20 different signs. And so we did a basic machine learning approach to the sign language recognition. This is primarily motivated by the fact that we didn't really have a lot of data. We only had 3 participants which were involved. So building very deep models was not really feasible given the amount of data that we had available. And we did an approach where we first extracted some features, then determined the optimal subset of those features, and then applied different classifiers and compared those performances. So in terms of features, we extracted some standard handcrafted features for micro-Doppler analysis. This would include features of the envelope, such as the maximum, minimum, and mean of the upper and lower envelopes, the difference between the mean of the upper and lower envelopes, coefficients like discrete cosine transform coefficients, which have shown to be effective in a variety of applications for micro-Doppler, as well as linear predictive coding coefficients. One thing unique to this work is that we also extracted data-driven features that were not obtained by using neural networks, which does automatic feature learning, but by using a genetic algorithm-optimized variant of male frequency Cepstral coefficients, which we've named frequency-warped Cepstral coefficients. I'm going to talk a little bit more about these coefficients in the next slide. But I just want to kind of finish the processing chain and mention that we did our feature selection by using an information theoretic approach called minimum redundancy, maximum relevancy. And we compared the performance for 4 different classifiers. Among these classifiers, as you'll see, we achieved the best performance actually with the random forest classifier. So I want to talk about, in a little bit more detail, these frequency-warped Cepstral coefficients. As I've mentioned, these are very similar to the Mel frequency Cepstral coefficients, which have been proposed for speech processing. The difference in what we're applying here on the radar data is that we've changed the way that this filter bank is being designed during the computation process of the Cepstral coefficients. And instead of using a Mel frequency scale to assign the center frequencies of the filters, what we do is we use a genetic algorithm to optimize the center frequency and the width of these filters. This is important because if you think about the frequency spread that you would get from a real RF sensor, they really have nothing to do with the way that our ear actually perceives sound. First of all, radar data can have positive as well as negative frequency, which is not the case when you have a MEL scale. And also, when you look at microdoppler analysis, a lot of the characteristics of the signal that we're using for the purposes of discrimination are actually hidden in the higher frequency regions of the data, not the lower frequency regions of the data. So whereas the MEL scale tends to have more filter banks at low frequency and fewer filter banks at high frequency, what we have found is that having the exact flipped situation, in other words, having fewer filter banks or fewer filters at the low frequency and more filters at the high frequency, is effective for the purposes of RF-based microdoppler analysis. And so the genetic algorithm basically uses classification accuracy to kind of optimize a set of 10 filters for this purpose, and we use those Cepstral coefficients as features in our algorithm. This signal processing flowchart summarizes the entire processing chain that we do for our data. So we initially take our RF time stream, we compute the FFT, apply an MTR filter, and convert this using a short time Fourier transform to a spectrogram so that we can actually look at our microdoppler signature. And then from that microdoppler signature, we extract our features. If we're only using one sensor, then we directly send it to the classifier. If we're looking at fusion of all of the data that's coming from each of these sensors, then we do feature level fusion. And as you can see on the next slide, we look at different case scenarios when we are either performing MTR filtering or without performing MTI filtering. MTI stands for moving target indication, and it's usually used when you're trying to eliminate the ground clutter returns or the stationary returns from our signal. So one of the things that we found that was interesting in our results is, first of all, that MTI filtering or ground clutter removal was not necessarily very effective across all of the different kinds of sensors that we looked at. So for example, if you compare using a clutter filter on the 77 gigahertz device, we actually found that not applying the clutter filter gave us better performance. Whereas for other sensors, like the low frequency sensor at 10 gigahertz, applying clutter filtering was much more effective. Our kind of hypothesis as to why this is the case has to do with kind of the level of fineness of detail that you can achieve from each one of these sensors. With a 77 gigahertz transmission, you get a much higher sensitivity to motion on your radar signal. So even a small motion can create a significant Doppler effect. And so our opinion is that if you apply clutter filtering onto this, you're actually getting rid of some of the signal components that might be due to very fine motions at the low frequency, and that these actually have a significant contribution to your classification accuracy, so that when you lose these signal components, your accuracy is hurt. The best performance that we achieved, obviously, is when you have feature-level fusion of all of these sensors, and this includes fusion of variants of when you're using clutter filtering and without clutter filtering. And so actually, we had 5 sensors, but we concatenated the features from 10 different data sets because we included the variation of whether there was filtering or not. And what we can see here is that actually applying the filtering gives us a slightly different perspective on the data, because the features that you're calculating are slightly different. You're picking up different things depending on whether you apply filtering or not. And when you fuse all of these features together, we get an overall classification accuracy of 72.5% over 20 ASL words. So after we did these initial results, we did look into some extensions of this work, which we're currently working on reporting, but I wanted to kind of give you a preview just in terms of the results, since I have the opportunity to talk to you now in the course of this conference. And that is that, when we collect a lot more data from imitation signers, we've developed a method where we could apply techniques such as domain adaptation and transfer learning so that you can actually use the data acquired from non-native signers and transform that to resemble the data from native signers and get much higher recognition results than what we were able to report in this particular work. So our initial results show that we're able to get easily over 90% for 20 signs, which is a very good indicator that, it's an optimistic indicator that actually using RF sensing will be beneficial moving towards the future and have good contributions towards ASL recognition. We've also collected some new data sets that have to do with sequential classification and looking at whether we can discriminate signing from daily activities in the course of just our daily life, looking at sequential classification for bag of words, and as well as identification of words in connected discourse. I would just like to kind of state to all of the researchers who are listening to me that we're glad to kind of share our data and work with other researchers who might be interested in this field. So if you are interested in corresponding with us or getting more information about our current and updated results that have to do with RF-based ASL recognition, please feel free to reach out to me at my email address, scgurbuz@ua.edu, and please check out our website at ci4r.ua.edu. Before I leave, I'd just like to acknowledge our support from the National Science Foundation, as well as the contributions of our community partners, AIDB and Gallaudet University. And without further ado, thank you for listening to my talk, and I wish you all a great day. Bye-bye.